Welcome to Deep Dive into Knowledge.
How long can a human survive without food?
Welcome to Deep Dive into Knowledge. I would like you to take a truly quiet moment today to consider a highly familiar, everyday human experience. Think about the mild panic, the very specific anxiety that sets in when you miss a single meal. Picture a standard Tuesday. Perhaps you were delayed at a meeting or you were caught in transit on a train that has stalled somewhere between stations, and the usual hour for your lunch just passes by. Notice what happens in your body and your mind. There is a subtle yet undeniable physiological anxiety that begins to creep in. You might feel a slight tremor in your hands. A fog of distraction settles over your thoughts, making it difficult to focus on the spreadsheet in front of you or the conversation you were trying to have. You become irritable, deeply focused on the immediate need to find sustenance. When you truly observe it, modern human life is entirely structured around the constant, predictable arrival of breakfast, lunch, and dinner. We build our daily schedules around these anchor points. We design our cities with cafes and restaurants on every corner. We construct our entire social rhythms around the fundamental assumption that food is always imminent. Whether you are at home, at work, or traveling, you are never truly far from your next source of energy. And because of this constant, uninterrupted feeding, we have developed a profound illusion of our own fragility. We feel as though we might genuinely break or collapse if we were to skip a day of eating. We interpret the rumbling stomach not as a gentle biological reminder, but as an absolute emergency siren. We believe we are delicate creatures, constantly teetering on the edge of depletion. If we do not eat by 1 o'clock, we feel as though our systems are shutting down. Yet beneath our modern skin, beneath the comfort of our carefully scheduled lives and our stock refrigerators, there is a dormant, ancient machinery waiting in the dark. It is a hidden architecture woven perfectly into our cells. It is a biological failsafe designed not for the overwhelming abundance of today, but for a harsh, unforgiving world where food simply stopped. It is an intricate system that most of us will never fully activate, a silent guardian that waits for a famine that, for many of us, never arrives. It is a subtle, unsettling wonder to contemplate what actually occurs when the refrigerator is finally empty, when the crops fail, and when the body slowly realizes that no help is coming. What is the sequence of events when the modern world falls away and the ancient biology takes over? We walk around every day carrying this invisible armor, completely unaware of the extreme conditions we are built to survive. So let's step into that darkness together. When the food entirely stops, what is the first thing our body actually does in the dark?
Right now, at this very moment, your body is operating on a very specific, readily available fuel source, which is glucose.
Right.
That glucose has been carefully extracted from whatever you consumed during your last meal. But when the food entirely stops, the body doesn't panic. It simply initiates the first phase of a highly orchestrated metabolic response. We call this period glycogenolysis, and it governs the first 24 hours of fasting.
Let's pause right there just to make sure we're completely clear. Glycogenolysis, that sounds quite technical. What exactly is happening in that first phase?
Essentially, it's the process of the body turning to its short-term storage. Assuming you don't eat again, the free-floating glucose in your bloodstream will run out in approximately 4 hours.
Just 4 hours?
Yes, roughly 4 hours. And at this precise threshold, your liver steps in. The liver acts as a profound chemical storehouse, and it begins to systematically break down glycogen, which is simply the stored form of sugar to carefully maintain your blood glucose levels.
So after just 4 hours, the immediate fuel is gone, and the liver essentially opens up a backup tank to keep the engine running smoothly. How much fuel is actually in that backup tank?
To understand the scale of this, we must look at the mathematics of human energy. In a normal adult weighing 70 kilograms, there are only about 8,000 kilojoules of glycogen stored in the body.
Okay.
And here's the interesting part. The liver doesn't hold all of it. The vast majority of this reserve is actually locked away in the striated muscles.
And when you say striated muscles, you're referring to the skeletal muscles, right? The muscles we actively use to walk, lift things, and move around.
Exactly. The muscles attached to your skeleton, they hold onto that glycogen tightly because they need it for movement. The primary reason this glycogen must be so carefully rationed by the liver, however, is the immense energy demand of the human mind. You see, the brain is an extraordinarily demanding organ.
In what way? I mean, we often think of physical labor as the thing that burns the most energy. How demanding is the brain when we're just sitting still?
It's staggering, actually.
Yeah.
The brain alone consumes about 18% of your entire basal metabolic rate.
And basal metabolic rate, just to be precise, is the energy your body burns just to stay alive, right? Like keeping the lights on in an empty house.
That's right. The energy required for your heart to beat, your lungs to expand, and your cells to function while you are completely at rest.
Right.
If you consider a standard daily energy intake of 1,800 kilocalories, the brain demands 324 of those kilocalories strictly for itself. In physical terms, that equates to exactly 80 grams of pure glucose dedicated every single day just to keeping your mind running, calculating, and remaining conscious.
80 grams of pure glucose. If you picture that, it's like a small mound of sugar sitting on a table, completely dedicated to fueling our thoughts and our consciousness for a single day. The brain really is an energy hog. It demands so much, even when the body is sitting entirely still.
It is. And during this first 24-hour period, the liver is working quietly to ensure the brain receives its 80 grams, maintaining the complete illusion of normalcy.
That's a fascinating way to frame it, the illusion of normalcy. It makes one reflect on the momentary mental clarity some people report when they try short-term fasting. People often say they feel incredibly sharp after skipping breakfast and lunch. I suppose the body is just running flawlessly on its immediate reserves, sustaining the illusion that everything is absolutely fine. The body hasn't yet realized that food isn't coming.
Precisely. The system is designed to handle short gaps seamlessly, but this illusion can't last forever. Those stored kilojoules in the muscles and the liver are finite.
Which brings us to a critical threshold. If the liver only has enough stored sugar for roughly a day, what happens at the biological pivot point? What occurs on day 2, when that 24-hour clock runs out, the glycogen is entirely gone, and the body must finally face the reality of starvation? Does it just crash?
No, it doesn't crash. When the glycogen reserve is exhausted, the body executes a magnificent systemic pivot. This is the great shift into phase 2.
Phase 2.
Yes. This period is defined by ketosis and fat metabolism, and it can last from day 1 to well past day 40. It's vital to understand that this isn't an emergency malfunction or a biological failure. It is a highly evolved feature, an ancient adaptation that allows a human being to survive for weeks without eating a single morsel of food.
So it's not the body breaking down, it's the body switching to a completely different operating system.
Yeah.
How does that shift actually work once the sugar is gone?
When the glucose runs out, the liver fundamentally changes its operation. It stops looking for sugar and begins breaking down your stored fat in a process known as ketogenesis.
Ketogenesis.
Exactly. The liver takes fatty acids and converts them into alternative energy molecules called ketone bodies. Specifically, these are beta-hydroxybutyrate, acetoacetate, and acetone.
Ketone bodies. You can almost think of them as a premium alternative fuel. It's quite literally like switching a hybrid car from a petrol engine over to its electric battery. But why can't the brain just burn the fat directly? Why does the liver need to manufacture these ketone bodies first?
That is the crucial evolutionary hurdle. The brain is protected by a highly selective membrane called the blood-brain barrier.
Right, which keeps out toxins.
Yes, it prevents toxins and pathogens from entering the neural tissue. And regular fatty acids simply cannot cross this barrier. They are too large and structurally incompatible. But ketone bodies possess the rare chemical ability to cross that barrier seamlessly. The liver is essentially refining the crude oil of your body fat into a high-grade aviation fuel that the brain can actually accept.
That's incredible. So the body is actively refining its own fuel on the fly. How long does it take for the brain to adjust to this new electric battery, so to speak?
The timeline of this shift is deeply impressive. After fasting for just 3 days, the brain transitions to drawing 30% of its energy directly from these ketone bodies.
30% in 3 days?
Yes, and by day 4, this adaptation leaps dramatically. The brain may derive 70% or more of its energy from ketones.
Wait, 70% of its energy from ketones by day 4? That's a massive biological pivot. How does that affect the 80 grams of glucose the brain was demanding back in day 1?
It changes the mathematics of survival entirely. By transitioning to ketone bodies, the brain's demand for pure glucose drops from that massive 80 grams a day down to a mere 30 grams.
That's a huge reduction.
It is a profound biological victory. Because the brain requires so much less glucose, the body is no longer forced to break down its own skeletal muscle at a high rate to manufacture sugar. By switching fuels, the brain is actively telling the body not to destroy its own muscles. It protects your strength by burning your fat instead.
That's a profound shift in perspective. The brain lowers its demand for sugar to protect the muscle so you can keep moving. What does this look like in terms of weight loss? People often experience a rapid drop when they first stop eating.
Yes. During the first 5 days of this phase, a person will typically observe a rapid weight loss of 1 to 2 kilograms per day. However, most of this initial loss is simply dehydration and shifting electrolytes.
Because the glycogen holds water.
Exactly. Glycogen holds a lot of water, so when it burns away, the water goes with it. As the weeks progress, the body enters a state of deep energy conservation, and the weight loss slows down to a highly conserved, sustainable average of just 0.3 kilograms per day.
Only 0.3 kilograms a day. It really is an extreme power-saving mode.
To put this evolutionary superpower into perspective, consider the animal kingdom. If a lion, an apex predator, goes without food for 3 days, it becomes significantly weakened. It's still functional enough to attempt to hunt, but its physical decline is rapid.
Right.
A human, however, who hasn't eaten for 3 days is merely completing the transition into ketosis. Thanks to this mechanism, the starving human retains full cognitive function, full mobility, and the clarity required to continue hunting, foraging, and solving complex problems in the face of profound scarcity.
That is an extraordinary comparison. The idea that a terrifying apex predator, like a lion, would be weakened and declining, while a human being is quietly unlocking an evolutionary superpower. It fundamentally changes how we view our own biology. We really aren't fragile at all. We are walking, remarkably efficient batteries, uniquely designed to outlast the empty periods of the natural world. If the body's protecting its muscles and only losing 0.3 kilos a day, we're talking about a vastly extended timeline. It leads one to wonder just how far this hidden machinery can actually be pushed. What is the absolute limit a human can survive in this suspended state of fat burning?
The absolute limits of human survival in this state are governed by a very simple metric, which is initial body composition. The duration you can survive is directly tied to the volume of fat reserves you hold when the starvation begins. It's simple arithmetic. Modern artificial intelligence models analyzing vast amounts of historical and biological data predict a 95% survival rate for humans after 30 days of total starvation.
30 days.
Yes. However, this probability drops precipitously as time goes on. By day 60, the models predict only a 10% survival rate, primarily due to the onset of critical organ failure.
Does this timeline differ between men and women?
Yes, it is noted in the biological data that biological females may generally withstand starvation slightly longer than males. Their bodies typically carry a higher percentage of body fat, and they metabolize it in a slightly different, highly conserved manner due to evolutionary adaptations tied to reproduction and survival.
So roughly 30 to 60 days for the average person before the system begins to fail. But there have to be exceptions, right? What is the extreme edge of this biological capability?
When we speak of extreme limits, we must discuss the astonishing, meticulously documented medical record of a Scottish man named Angus Barbieri. From June of 1965 to July of 1966, under strict medical supervision, Angus Barbieri consumed absolutely zero solid food. He fasted for 382 entire days.
Let's slow down and process that for a moment. 382 days. That is over a full calendar year without a single meal. How is that physically possible without organ failure?
Because he began his fast at an extreme weight of 456 pounds. He possessed massive fat reserves. Over the course of more than a year, he survived entirely by burning that fat, eventually ending his fast at 180 pounds.
Goodness.
He lost 276 pounds simply by allowing his ancient biological machinery to operate. Throughout the 382 days, he consumed only 0-calorie liquids: tea, coffee, water, and soda water. He visited the hospital regularly for checkups, and his doctors monitored his electrolytes closely, but the energy keeping him alive came entirely from within.
It's difficult to even comprehend that scale of time. To exist for more than a year with the digestive system entirely silent, living purely off the stored energy beneath one's own skin. It's a profound testament to the body's resilience. But you mentioned he was drinking liquids. And that brings up a crucial distinction, doesn't it? We've been talking about the absence of food. What happens when we remove water from the equation?
That brings us to the absolute, immovable boundary of human endurance, the water paradox. While the body can survive for months without food by consuming itself, the absence of water changes the equation entirely. Without water, the survival timeline plummets from months to merely 3 to 7 days.
3 to 7 days, that's a staggering drop. Why does the lack of water break the machinery so quickly?
Every single metabolic process we've discussed, including the breakdown of fat into ketones, requires water. It's the medium in which all cellular communication happens. It's essential for blood circulation, waste elimination, and basic cellular function. Without it, the body succumbs to severe hypohydration.
And hypohydration is essentially the clinical term for a critical lack of water inside the body's tissues.
Exactly. Furthermore, the starvation process itself creates a fairly large urinary nitrogen excretion.
What does that mean exactly?
This nitrogen release is a clear indicator that proteins are being broken down, and excreting that nitrogen takes a significant amount of water with it. There's also a severe mineral loss concomitant with this water loss. Dehydration becomes lethal long before the fat reserves are ever depleted. You can have hundreds of pounds of fat left to burn, but without water, the engine seizes entirely.
It really highlights a profound paradox. We can endure the total absence of food for seasons, but the absence of water breaks our biological machinery in a matter of days. Water is the ultimate tether to life. I imagine there are claims of people surviving without water, given how people love to push the boundaries of extreme survival. Are there any documented outliers?
There are extreme outliers in the historical record, though they must be approached with scientific caution. In 1970, a man named Stephan Taylor in New Zealand reportedly survived 40 days consuming only a single glass of water daily. There is documentation of a South African woman who survived 102 days on just water and soda water.
That's astonishing.
It is. And then there are the deeply controversial claims, such as the Indian yogi Prahlad Jani. Scientists from India's Defense Institute of Physiology and Allied Sciences studied him in 2003 and again in 2010. They noted he possessed some extreme form of adaptation to starvation and water restriction. During a 15-day observation, he allegedly didn't eat, drink, or use the toilet, claiming to have lived this way for 76 years.
76 years without food or water. That sounds less like biology and more like mythology.
Yes, those extreme claims remain entirely unverified by independent, rigorous scientific researchers. Setting aside the unverified, the biological truth remains exactly as we discussed. Water is the ultimate tether to life.
So, assuming one has water, the physical body can sustain itself for these vast stretches of time. But these long weeks and months in the dark lead me to think about the internal experience of the individual. We've discussed the physical body, the liver, and the ketone bodies protecting the brain's energy supply. But what about the consciousness trapped inside that starving body? Does the mind remain entirely intact and unaffected while the body slowly consumes itself? What happens to human psychology during this deep, prolonged metabolic shift?
The consciousness certainly doesn't escape unscathed. It's profoundly altered by the very mechanisms keeping it alive. As the body enters this deep phase of starvation, it doesn't simply burn reserves at a normal pace. It fundamentally adapts, entering a state of deep metabolic slowdown. Think of it as an extreme emergency power-saving mode.
So the body starts shutting down non-essential functions to conserve the battery. What does that actually feel like for the person experiencing it?
Over time, this slowdown permeates every tissue and organ system. The heart rate plummets to preserve energy. Core body temperature drops, leaving the individual feeling constantly, pervasively cold because the body refuses to expend precious fuel on heat production.
They just can't get warm.
Exactly. The digestive system essentially goes into hibernation, halting the secretion of enzymes and physically shrinking the stomach. And along with this physical depression comes a profound psychological apathy. The individual becomes intensely fatigued, weak, and utterly uninterested in the activities that would normally define their life.
It sounds incredibly isolating. To be physically cold and emotionally hollowed out, how do we know so much about the specific psychological toll of this state?
We know the detailed psychological toll largely due to a remarkable study called the Minnesota Starvation Experiment, which was conducted during the Second World War. Researchers placed a group of healthy young men on a semi-starvation diet of roughly 1,500 calories a day for 6 entire months.
Wait, 1,500 calories a day? That doesn't sound like complete starvation. Some people eat that much on a standard modern diet.
It wasn't complete fasting, no. But for active young men whose bodies required 3,000 calories to maintain their weight, it was a slow, grinding starvation. It was specifically designed to mimic the conditions of famine taking place in war-torn Europe.
I see.
The psychological warping they documented in these men was severe and highly disturbing. The minds of the participants became entirely consumed by the concept of food. It became an overwhelming, inescapable obsession. They thought about it constantly, they dreamed about it, and they began exhibiting bizarre behaviors. For instance, obsessively collecting cookbooks and recipes, despite having absolutely no ingredients to cook with.
There is a tragic, almost dark humor in that. Collecting cookbooks when you're starving. It's as if the mind is trying to solve a problem that the body can't fix, hoarding the idea of food because the physical reality of it is denied. Did their personalities change beyond the obsession with food?
Dramatically.
Yeah.
Their personalities fractured. They developed severe irritability, anxiety, and depression. They were easily distracted, suffering from an immense lack of energy. They lost interest in romance and socializing and in their own personal development.
That's devastating.
Alarmingly, for many of the participants, the experiment resulted in long-lasting eating disorders that persisted for years after they returned to normal diets. The trauma of the deprivation rewired their relationship with sustenance permanently.
It's a profound tragedy to consider the mind slowly turning against itself. To be trapped in a state where the consciousness becomes utterly obsessed with the very thing it can't have, collecting recipes like precious artifacts while the body is wasting away. The evolutionary machinery protects the brain's physical structure with ketones, but it clearly can't protect the human spirit from the grinding reality of deprivation.
That's a very accurate assessment. This psychological decay makes perfect biochemical sense. While ketone bodies are a miraculous evolutionary bridge, saving the brain from immediate death, prolonged reliance upon them takes a toll. As the starvation drags on, and especially as the body begins to run low on its optimal fuels, the lack of abundant glucose leads to a severe and measurable cognitive decline. The mind survives, yes, but it becomes a shadow of itself, warped by obsession and dulled by the absolute imperative to conserve energy.
So the body slows down, reducing the heart rate, dropping the temperature, and dimming the light of consciousness to a bare flicker. It's clearly preparing for a final stand. Which brings us to the inevitable, heavy question. We know the fat reserves, even in someone like Angus Barbieri, must eventually run out. What happens when that deep well is finally empty? What is the final, fatal phase of this process?
When the fat reserves are finally exhausted, the body crosses a terrifying and irreversible threshold into phase 3. This phase is defined by protein catabolism.
Protein catabolism, let's make sure that's clear. When you say catabolism, you're essentially saying the body is actively breaking down its own proteins to survive, right? It's literally eating itself.
Exactly. At this point, the biological fail-safes have failed. The body has absolutely no choice left but to begin cannibalizing itself for energy. Because the brain and essential systems still require a baseline of fuel to function, the body targets its largest remaining source of protein, which is the skeletal muscles.
Right.
The visible hallmarks of starvation emerge very rapidly here. This is when you see the characteristic protruding bones and the deeply wasted limbs. An individual quickly loses all physical strength. They become unable to walk, unable to stand, and eventually unable even to sit upright without physical support.
So the body consumes the very muscles it worked so hard to protect during the ketosis phase, but it doesn't stop at the skeletal muscles, does it?
No, and that is the true tragedy of phase 3. The body doesn't distinguish between skeletal muscle and vital organs. The heart, fundamentally, is a muscle. As protein catabolism accelerates, the body breaks down the tissue of the heart itself to extract amino acids.
It breaks down the heart.
Yes. The heart muscle weakens profoundly. Its mass literally shrinks. Blood pressure drops dangerously low. As the cellular tissues degrade, massive electrolyte imbalances occur, leading to cardiac arrhythmia. Ultimately, cardiac arrest is the most common physiological cause of death in starvation.
The body eats its own heart to keep the brain alive. That is deeply sobering. What happens to the rest of the body's defenses during this phase?
Simultaneously, the immune system undergoes a total collapse. The body simply can't manufacture new immune cells, like white blood cells, without protein. Wounds cease to heal. Minor infections that the body would normally eradicate with ease suddenly become life-threatening. The nervous system degrades, leading to peripheral neuropathy, the loss of basic reflexes, and eventually the complete loss of consciousness. In a leaner person who hits this phase much faster due to smaller initial fat reserves, this sequence of total organ failure arrives much sooner.
It's a devastating cascade of failures. But there's another element to this that is perhaps even more tragic. We've talked about the darkness of starvation, but what happens when the light finally appears? When rescue finally does come for those who have endured this, why is salvation itself sometimes deadly? How can a meal kill someone?
It is the most dangerous and counterintuitive aspect of this entire process, and it occurs precisely at the moment of rescue. If a profoundly starving person is suddenly presented with a large, normal meal, it can trigger a potentially fatal condition known as refeeding syndrome.
Refeeding syndrome. What exactly is happening chemically that turns food into poison for a starving body?
To understand it, you have to look at what the body's chemistry has become during that long metabolic hibernation.
Yeah.
During starvation, the body's electrolyte concentrations, specifically potassium, phosphate, and magnesium, shift to a very fragile, low-level equilibrium. They are barely maintaining the electrical signals needed to keep the heart beating.
I see.
If a person suddenly consumes a large amount of carbohydrates, the body forcefully attempts to restart its standard glucose metabolism. To process all those new carbohydrates, the pancreas releases a massive sudden spike of insulin.
And insulin acts like a key, right? It opens the doors of the cells to let the sugar in.
Yes, but it doesn't just let sugar in. This sudden insulin rush aggressively drives the already critically depleted potassium and phosphate out of the bloodstream and forces them into the cells alongside the glucose. The result is an immediate catastrophic crash in blood electrolyte levels. The blood is suddenly stripped of the minerals it needs to conduct electricity.
Which affects the heart.
Exactly. This sudden imbalance can trigger instant cardiac arrhythmias, severe respiratory failure, violent seizures, or sudden death.
It's heartbreaking. The body is so desperate for the food, but the machinery is too fragile to process it. It simply shorts out the electrical system of the heart. This must have been a horrifying reality during historical famines or conflicts.
It was. This is the tragic historical reality we witnessed at the end of the Second World War. When Allied forces liberated the concentration camps across Europe, well-meaning soldiers and rescuers immediately provided the starving survivors with normal, heavy meals: chocolate, bread, canned rations. Unknowingly, they triggered refeeding syndrome.
That is awful.
Many survivors died from the very food meant to save them, simply because their bodies couldn't handle the sudden metabolic shock. Because the digestive system has essentially forgotten how to process meals, and the cellular chemistry is so fragile, medical protocols today dictate that refeeding must be exceptionally slow. It has to be meticulously monitored, often starting with tiny amounts of liquid nutrition, and scientifically calculated to prevent the body from shocking itself to death.
That's a vital piece of medical understanding.
It is. You know, when we examine this entire biological sequence, from the liver's first subtle adjustments to the final desperate catabolism of the heart, it forces a deeply philosophical reflection on our modern existence. There's a profound, almost tragic mismatch between the biology we carry and the environment we've built. The very metabolic adaptations we've discussed today, the brilliant, sophisticated cellular engineering that allowed our ancient ancestors to survive brutal, seasonal famines, are the exact same physiological mechanisms that make modern humans so incredibly prone to weight gain and obesity. Our bodies are magnificent survival engines, precisely tuned for a world of extreme scarcity. They're designed to hoard energy, to effortlessly convert excess food into stored fat, and to fiercely protect those reserves at all costs. Yet we now exist in a world of overwhelming, unprecedented caloric abundance. We are essentially walking around in ancient arks designed perfectly to weather a storm of starvation, but we find ourselves adrift in an endless sea of plenty. The biology that once saved us is now the biology that burdens us, simply because the famine our cells are constantly preparing for no longer arrives.
That is a deeply resonant thought. We are walking around in ancient arks carrying a profound history of survival within our very cells, waiting for a storm that we've engineered out of existence. Today, we've traced an extraordinary journey. We began with the simple, familiar panic of a delayed lunch and ventured down into the deep, protective hibernation of ketosis. We observed how the body brilliantly alters its own chemistry to shield the mind, turning fat into a premium fuel to preserve our strength. We explored the vast, astonishing timelines of human endurance, marveling at how long we can survive on our own internal reserves. And finally, we face the fragile, tragic threshold where the body is forced to consume itself and where even the promise of food must be treated with the utmost caution. I invite you to take a quiet moment today to appreciate that hidden architecture within you. The next time you feel a slight hunger of a missed meal and you feel that familiar irritation creeping in, remember the silent, ancient wisdom perfectly coded into your biology. It is standing by, silently keeping watch, ready to carry you through the dark. Thank you for joining us on this deep dive. We'll return soon to uncover another hidden pattern woven deeply into the fabric of our lives.